All right, welcome back.
Hey.
There's more.
We're still here?
Whoa. This is about the best way I can think of to spend the Thanksgiving break, Jason.
I'm
is
so
making
happy
these
to be here.
videos.
Where is
It's
Allison
awesome.
and where is Alexandra?
I got this, one of those Instagram things that had like a beach and a tropical drink in
Wow.
it. Yeah, and here we are.
It snowed this morning.
It snowed, yeah, that's true. It was pretty sad. Anyways, enough of that. We were talking about validation in mechanical systems. We've already talked about sort of energy conservation. We're going to now talk about the idea of doing qualitative first principle validation, and the sort of key example we're going to talk about for that is the idea of doing limiting cases. So this is something we've already done some of before. So for example, with thermal stuff, what happens if you turn off the sun? Well, if you turn off the sun, then you're not putting any energy into the house, so the house ought to go to the same temperature as the outside, right? So it's an example of limiting cases. They're particularly useful to do for mechanical systems. And so to do them for mechanical systems, let's actually go back to the hopper example that we talked about in class. So let me remind you of that example. So we have the rod, right, that sort of holds a reaction mass ring. And then there are springs that attach that reaction mass ring to the top of the rod with the idea that we pull this down, let it go, this thing goes up, and it beautifully shoots into the air.
Yeah.
Right? So what would we be limiting cases where we sort of know what this ought to do? I mean, the definition of a limiting case is that we sort of know the answer without doing the math.
Mm-hmm.
Because if you know the answer without doing the math, and then you check that your math gives you that answer, you can have some confidence you've actually done your math right, right? Or that you've set up your model in a way that actually makes sense. So suggestions, what are some limiting cases we could do?
Well, let's think about the mass of the rod and the mass of the ring, right? So if we had a really heavy rod, what would happen?
Well, let's see. If we made the rod really, really heavy, that would be like basically kind of attaching
Almost
the
like
rod
anchoring to the ground, right?
Be anchored to the ground. So I would think that so let's actually write M rod and M ring here, and we'll sort of make a table.
Yeah.
And what do we expect, right? Well, let's see. If M rod is big and M rod is small, or M ring is small, we expect the ring to basically jump up and go up and down and up and down and up and down. And presumably if this thing has a big enough mass, it never gets lifted off the ground at all.
So that phase of motion where the rod is off the ground just never happens.
We'd also expect that because the rod is never moving, the ring is just going to oscillate up and down the same forever. Right? Okay?
Okay, well, let's reverse that. So what about if we have a small ring, a small rod, and a big ring?
Well, it almost seems like there's a case where if you made the ring big enough, that it would be really boring.
Yeah, because nothing's
Right?
gonna
Like if
happen.
I made this ring out of granite or something, it would just sit there on the ground and I'd just have these stretched springs.
Yeah.
Right? So everything just sits there.
Yep.
Okay? So those two seem like they'd be sort of easy to check.
Yeah.
What if we turned off gravity? What would happen then? That's all. I always feel like it's useful, like for limiting cases, it's useful to think about what happens if we get rid of X.
Yeah. So we turn off.
So no gravity.
So once you launch it, it's going to keep going up forever, right?
So it should keep on going up forever. When should it leave? When should the rod leave the ground?
Well, one thought would be immediately. So as soon as the thing starts pulling back, there's no normal force on the thing.
Well, there'd be a normal force, right?
because it is on the ground.
Well, you've got this. It's on the ground. The spring is pulling the rod down.
Right.
So it's still going to stay in contact with the ground, but I think as soon as the ring goes past horizontal,
Right. Then you
right?
start.
Then
getting
you've got a
forces going
force up from the spring. The only other force present is the normal force, which can only be up. So there's got to be zero normal force in that case. So it's going to go up forever, and it'll leave the ground when the springs are horizontal, or when the springs break horizontal. Right. Other limiting cases we could do?
You want to think about when the masses are equal? Is that a useful limiting case?
So let's see, if the masses are equal, what's going to happen then?
So they're gonna pull against each other. Once the thing has left the ground, they're gonna pull against each other equally. Right, so they're both gonna oscillate.
Yeah.
Is there anything we can say about their oscillations?
I mean, it seems like you would be able. My intuition says they're going to oscillate at the same amplitude, but I think we'd have to run some math to actually see if that
Yeah,
was
that's,
right.
as a limiting case, that kind of stretches
Yeah.
my ability to do
Yeah.
math in my head.
I mean, I'm pretty sure that you actually, if you run the numbers on that, you'll find that they should oscillate at the same amplitude. And you would be, I think you could make that argument by going to a center of mass frame for it, but yeah, I think that's a stretch.
Yeah. Anything
What
else?
happens if I make this reaction mass be zero?
Then you're certainly not going to get off the ground.
Yeah.
Right. Anything else we can say about that situation?
Well, that's a weird one, because now we've got a force that's being attached to zero mass.
Yeah.
And so that makes this thing have an infinite acceleration. You know, sometimes making masses zero isn't the best idea.
Okay.
So I would say it's actually, that's a good example of a limiting case that kind of makes your head hurt because it forces some things to go to infinity.
Yep.
So I would say maybe making mass be zero is not such a great idea.
What about the rod? Make the rod mass zero.
Well, if the rod mass were zero, then pretty clearly it would get lifted off the ground just as soon as the ring goes past vertical or past
So
horizontal.
just like the zero gravity case.
And then at that point, the rod's not actually going to be able to stretch the spring at all. So I think that the ring will just happily fly through the air.
Kind of like a.
Just like it would actually be like as if you basically took it and you said, okay, I've got a sort of spring and I've got a mass on it. I compress it and I let it go. It's just going to fly and it's going to fly through a parabolic
it's a
trajectory.
projectile.
So that's actually, maybe that's a good limiting case of sort of saying if we make m rod be zero and m ring be non-zero, then we should get sort of simple parabolic.
You have a projectile ring.
Right. Okay. Yeah, and that one I can buy. So I think the lessons here are, first of all, that be careful about what you set to zero and make sure that you don't get sort of infinities. Like when you set something to zero and then you've got it in a denominator, bad things happen. And I think we sort of saw that when we tried to make the ring mass be zero. On the other hand, turning things to zero, like turning off gravity, should be helpful. Like we know what ought to happen here. When we look at the sort of ratios of things, that's often a helpful thing to do. So, and at this point, I think we've made a set of predictions. We probably need to go and actually run some simulations to see if these predictions made sense. But they seem like they're pretty useful predictions to actually compare against the simulation.
I agree.